Welcome back, everybody. Hope you enjoyed your cup of coffee. Get your attention back on track. Make sure that everyone's awake. All right, great. Just before the break, we had finished with our chapter 4. Right? Through the last 2 days, we've been looking at what is GIS, GIS in the database, how we get our information into GIS, the R catalog application, which is our ArcGIS database management program, and then the ArcMap application as well. How do we actually view that information and come across from the table into actual visualization. Right. So in this chapter, we're actually going to move on and have a look at exploring projections in GIS. Alright, so before we do, I want to ask you, when you decided to come on this training and we sent out some information to you, what was one of the first things that you asked us about? What did you need to know in order to come on the training?
Where is the venue?
Where is the venue? Okay, where am I going? And how did you guys get here? When you arrived here on Tuesday, where did you come from and how did you get here?
By home.
You came by road, right? Yes, Sipo?
I drove, but with the help of my GPS.
Okay, so you used a GPS. Did anyone else use anything to get here? Any other information? Yes, Ross?
I used a map.
A map. Okay. So we use things in order to be able to show us how to get to certain places. So location to us is a very important concept in everyday life, right? In GIS, location is the most important concept, right? When we're working with geographic information, we're working with entities that have a geographic component to them. And what geography is location. Your GPS uses geographic coordinates. Your map shows you a place that you're trying to get to. Okay, all of these things rely on location. So we're going to have a look at what is location and how we actually translate this location into a workable piece of information that we can visualize. All right. So the objectives of this lesson will be to identify the principles of location. What is location all about? We're going to understand what a map projection is. We're going to look at how map projections introduce spatial distortion. And then we're actually going to apply different projections and see how they manipulate our data in the software. So let's have a look at defining our location. First of all, can anyone tell me where that place is? Having a look at that slide. Where is that place? Come on, guys.
Cape Town. In the middle of the right-hand side.
In the middle of the right-hand side. Okay, anyone else?
No.
No? No? What do we need before we can define location? Yes?
Point of reference.
A point of reference. Excellent. We need something to refer that place to. Okay. What other aspects come into it? If I look, okay, I've got a point of reference now, so I've got a nice big tree there to show you. Okay, my place is now close to a tree. What other aspects do we need? Yes, right.
Sort of values, distance values.
Distance values. Okay, what else could be helpful?
Scales.
Scales, all right. Size, close to, far away from. Okay, another aspect of distance. Yes?
We need to know where that tree is actually.
Okay, you need to know knowledge. You need to have a knowledge of that landmark. You need to have a knowledge of where that tree is. All right. Another thing is direction. For example, east, north, south, west. The reason why we don't use a location system like this in GIS is that it requires a knowledge of landmarks. I'm in the southern hemisphere, I'm in South Africa. Okay. I see things differently to someone standing in the northern hemisphere. Right. So in GIS, we needed to develop a system that everybody around the world could use to locate specific entities. A reference grid that they could place their places on. So everyone had the same point of reference. All right. So something that's very familiar to you, if you're not a member of the Flat Earth Society, is the fact that the Earth is actually round. Right. We use two main lines of reference on the Earth. Can anyone name them for me? Yes.
Longitude.
Okay, longitude and latitude. Excellent. What are the main lines of
I wanted to say
longitude?
the equator, isn't it?
The equator is one of them. All right, and the Greenwich Meridian. Perfect. Our two main points of reference on our round Earth. Everyone agree?
Yes.
Right. In addition to our equator and our prime meridian, we have lines of latitude, which we call our parallels, and lines of longitude, which we call our meridians. Okay, everybody happy with this from geography? There's nothing new. All right, perfect. So our spatial reference system in GIS, in terms of our geographic, our 3D world, is latitude and longitude. Right. So we work with degrees, minutes, and seconds. Okay. If you imagine the world, if you imagine a globe, all right, going back to your mathematics days, a circle has 360 degrees. Okay, my globe. So when I work with lines of latitude and longitude, they are determined if you had to cut this globe in half. If we had to cut it down, let's just cut a segment out of it. Right. And then I had to measure, there's my equator. I cut a nice little segment out of there. If I had to measure from my equator up to where I've made my cut, where my cut stops, and draw a line around the Earth, that line where it would touch the circle is giving me an angle. It's giving me 30 degrees, 45 degrees, 60 degrees. Right. So that's where we get our degrees of latitude and longitude from, is that angle that you get out of the 360 degrees of the globe. Makes sense? Okay. So the angular units of measure, longitudes are meridians, latitudes are our parallels. Latitude, latitude, easy way to remember it. Okay. So now, how do we go from taking this and making it something that we can work on a flat surface? Because when you speak to somebody in everyday life, do you say, okay, Stimbiso, you coming from Midrand, I'm in Sandton. I'm 1 degree, 2 minutes, and 40 seconds away from you. Okay. We don't measure distance in terms of our latitude and longitude. What do we measure it in? Meters. Kilometers. All right. So this isn't a system that's going to be useful to us when we want to make measurements and do calculations. So we have to take this and turn it into this. All right. Something that we can lay flat on a surface, take a ruler, make a measurement, define a distance. Right. So that is what a map projection is. It's going from our 3D Earth, okay, to a 2D representation of that Earth. All right. That's simple. Luckily for you, the software is designed in such a way it does it automatically. Right. You don't have to actually sit down and do all the calculations for yourself. So map projection transplant our locations from our 3D globe onto our 2D map. So we can make distance measurements. There are various different types of map projections that we use. Okay. The first type that you get is a cylindrical projection. So I would take my piece of paper, imagine this being a blank piece of paper, and I would put it around my globe so that it fits nice and tightly. And I would shine a light through the middle of that globe. Okay. And where that light shines out onto my paper, I can trace the Earth. Depending on where I am sitting on the Earth, if I want to be very accurate along the measurements of my equator, I can use the normal cylindrical projection. If I want my measurements to be accurate around the poles, I can do what is called a transverse cylindrical. So I just turn it. Or oblique, or any other way. Depending on where you're sitting on the Earth is going to determine what projection style you're going to use. The second style of projection that we have is called conical. So it's like taking a little party hat and putting it on top of my Earth. He's having a lekker jaw now. Right. Party hats are very good for our polar regions. Because where that cone is now touching my globe, that surface, is a very accurate representation of that data. Okay. So you'll find your conical projections very useful for places that are close to the North Pole and close to the South Pole. An example there, our landward conformal conic. And the third type we have is our planar projections. Okay. Planar, anyone want to take a guess? Just by looking at the name? Flat, plain, paper. All right. So just a nice flat piece of paper that I have. I lay it against the side of the Earth, on the top, right? You get polar planar, equatorial planar, oblique planar. Other ways to look at it, you get a tangent planar, whereas the paper just sits against the side and you trace. Or you can get a secant planar, where it actually cuts through on two different parts. Alright, so you get an accurate representation on the parts where it cuts through the globe. Any questions? You guys happy? Alright. So those are the three main projection types that you get. There are additional ones, and they are described in the literature, and they are available on the software. Okay, so I'll show you when you do your exercises where you can actually find that information. Alright. So now that we know what type of projections we can use in GIS, it's important to know that projections can introduce spatial distortion. If I'm going from my 3D model to a flat surface, if you imagine the Earth as if you blow it up like a balloon, right? If I had to blow this up like a balloon, and then I had to squash it, what is that going to do to that information on that balloon? How is it going to change it? Right, so before you answer, I want you to get into your groups, right? First group, second group, third group. Get together, brainstorm a little bit. Tell me what you think would change when you're going from that 3D model to your flat 2D surface. What discrepancies will be brought into play? Right. Do you guys understand? You good?
Yeah.
Any problems? Good? Yeah, that's good. All right. Okay. Got some ideas? Great. So let's start off with your answers, right? This is Percy, when you asked earlier in the expectations yesterday, you said, how do you go from our 3D to our 2D? This is exactly how we do it. Right. Super, so who's got something for me? When we squish our globe, what happens to it? Yes, Adam?
Well, we got distances are distorted.
Okay, so distance. Great. What else?
Elevations are lost.
Elevations, okay. Right, what else? Anyone else?
Direction.
Direction, okay. You can see my direction is going a bit off there as well. Right. Anyone else? Shape. Okay. The shape of our continents might change. Excellent. What else?
Area.
Sorry?
Area.
Area. Okay. Anyone got anything to add to that? Yeah, good. All right. So when it comes to distortion, when going from your 3D to your 2D, all right, we can work with all of these things. Every single answer has correct. Okay, very good. What we do, just to make it a little bit easier for us to remember, is that we employ something called an acronym. All right. And the acronym for distortion in GIS is that projections make geographers very sad. Okay. Because they distort shape, area, distance,